ממש משתדל שזה לא יהיה לא ב-12 ולא ב-15, כי יש לי ב-13 וב-15 מבחנים. אז ב-15 ספציפית אני ממש כזה לא יכול. אם זה יזוז שבוע קדימה או שבוע אחורה מבחינתכם, זה אצלנו או שיש לזה משמעות?
לא, אין משמעות. המגבלות הן לא שלנו במובן. כאילו, הבעיה היחידה שביקשנו בגלל לדחות,
כן, לא, זה היה ממש
פשוט
ביום
4
הראשון.
ימים אחרי תחילת סמסטר. וזה לא מספיק זמן עם המבחן. כל השאר ממש לא. אבל זה לא נראה לי סטרנג' שלנו.
יש עוד מגבלות.
נראה לי שזה בא
תודה.
Okay, good afternoon. I'd like to start. I just want to say first about the exam. The date that Neely was thinking of is not the 15th. I think that's what I mentioned last time. It was the 12th. But apparently for some of you, this might be a problem because of other exams. From the point of view of the Computational Neuroscience program, it's quite flexible because you don't have so many exams. I think the main difficulty is the exam not to come too close to the studies course, which is in March. So what I suggest is that you will discuss it between you at the break today and try to see if you can find a time which is convenient for everyone.
What are the restrictions? All dates in February?
I think the reason we did it in very early was that I would not be here, as I mentioned, but we realized this is not a big issue. So therefore, I think we're very flexible. I think it's just the exams that other people have here are the restrictions. Okay, so what we will do today. What we will do today is to finish our discussion on the reinforced algorithm, and this will end our discussion of supervised learning overall, and then we'll start the next chapter of the course, which has to do with decoding of neural activity. So let's finish with reinforce. So I first would like to remind you of the setup, which is a generalization of a setup that we discussed in previously. So we have examples x0, and then we have a network activity, which is a vector of activities of the units in the network. And for convenience, we denote by the concatenation of these two vectors x. We denote that as x. And this is like all the activity, the inputs to all the neurons in the network, and all the outputs as well. So, and all the intermediate activities. And the idea is that these are drawn from some distribution, and also the responses. This is different from things that we discussed before. The responses in the network are also stochastic. They're not deterministic. So we can say what is the probability of I will write it in shorthand now. What is the probability of y given x0? There's some probability of the responses given x0, but in fact, each unit in the network responds to its inputs, and we assume that the structure of connections between units is such that there are no loops. So so maybe I need to write it a little bit more explicitly. There is some probability of unit y, I being equal to y, given the inputs, but this relationship involves other units in the network or the inputs to the network in such a way that there are no loops, because otherwise we cannot prove. It's not well defined, and we will not be able to prove what we need to prove. Okay, so no loops. And then finally, there is some probability of reward given x and y. Given x. How did I write it? I just want to use the same notation. Yeah, I wrote x and y, but it's really x0 or y, and we could also write this as x. Okay, and then I described to you the reinforced algorithm, which is just to look again and again at examples drawn from the distribution, draw the output of the network, and update the weights in the following way. So the change in weight wij is equal to some constant, eta, times the reward, times eij, where eij is formally defined by an equation that I wrote. It's the derivative log pi of yi equals y, or yi, derivative of yi, log pi of yi x, and of course it depends also on the weights, with respect to wij. So we will look in a bit more detail in a moment what this actually means in a particular example. But for now, this is, if you know all these, if you know these properties, if you know what this is and you know what this is, actually if you know what this is all you need to know. If you know what this is, you have an expression for it, you can calculate also the expression for eij. And what I'd like to do now is to prove two things that I mentioned to you. So one is that the average of eij is equal to 0. And on the other hand, that the average of r eij is equal to the derivative with respect to wij r. So maybe I'll go through the proofs, and then I'll remind you again why this is useful. Okay? So let's go through the proofs for that. So maybe let's number them, 1 and 2. Okay, so I want to calculate the average of eij. So I'm going to average it now. In principle, we have to think, what do we mean when we write average? There are several stochastic sources of stochasticity here: the choice of the examples, the choice of the response given the examples. EIJ does not depend on the reward, so it doesn't care about the reward, but it cares about this and this. What I will do now is show that the average of this is 0 even given a particular example. So I will only average over the distribution of y given x and w. Okay? So we'll see that it's, or x0. Okay, so we'll see that we will show that this is 0 for any example. So what do I mean by this? So I need to do an integral over, so EIJ involves yi, right? So, but I can write, it's integral over dy, dy, p of y, the probability of y, given x and w. And we have here the derivative with respect to dwij log. When I write this, in principle, I should write here an integral over all the ingredients of y, but I really care only about yi. So I have here d to the wij log pi of yi given x and w with respect to dw. I wrote it already here. So now
So the average is over x0 or x, because here it's over here.
the average is over the distribution of y given x0.
But here it's
And I'm averaging over y. I'm doing an integral over y, the probability of y, and the quantity that I'm averaging, right? So this is what I mean when I'm averaging over the probability of distribution of y of some quantity. This is EIJ, and I'm running over all possibilities of y, weighted by the probability.
But here it's x0 and here it's x. So
Yeah, let's write it here, x0. Thank you. Okay, so now when I take the derivative of a log, what do I get? I get 1 over p. So here, you see, this is really like a product of the probabilities over all the y's. But we care only about the particular I that appears here. And the rest of them will just integrate to 1. So eventually we'll have here integral of p of yi. And when I take the derivative with respect to wij, I will get 1 over p times the derivative of p. So I will get something like integral dyi 1 over p times, p times 1 over p times log of p. I'm writing it without all the things in the parentheses, so this will cancel, and there will be here d to the wij. But note that wij appears only here, so I can take the derivative with respect to wij and put it here, because it does not appear in these expressions. Wait, no. I could, okay. In principle, what I should do is to write d to the wij of, so the derivative with respect to wij is, let's do it a bit more carefully. It's 1 over p times, we have here 1 over p d to the wij p, right? And now this cancels. And now I can take the derivative with respect to wij in front of the integral. I can replace the order of integration and the derivative. So I have here d to the wij integral dyi p of pi of yi given x0 w. Now what is this?
Why couldn't you do it before?
What I did, I don't know what I tried to do before. I think this is correct and makes sense, so let's stick with that. Right? I take the derivative, because p itself does depend on w. So when I take the derivative with respect to w, I have here 1 over p times the derivative with respect to w of p. Oh, it's fine, it's fine. Okay. I don't know. What's written now makes sense, so let's stick with that. So this is, what is this? It's 1. Now, I should say that I've been, what? Okay. Okay, so this is 1, and therefore the derivative with respect to wij is 0. So this is what we wanted to prove, that the eij on average is 0. And you see that it's 0 on average, given any example, it's on average 0. Okay, so this is 1. Let's do 2. Now I look at eij multiplied by r. So now I am going to take into account, when I do an averaging, I'll do the averaging both on p of x0 and on p of y given x0 and w, and on p of r given y, given the yes, but there is a hierarchy here in these distributions, that p x0 is chosen independently of anything else, y is drawn conditioned on x0, and r is drawn conditional on y and x0, or y with the definition of, or x, what we called x, right? So there is a hierarchy here, and therefore I can write this average taking that into account. I can write that this is, what I mean by this average is an integral dx p0 of x, x0, let's call this x0. And then there is an integral dy p of y given x0 and w. And here y is a vector. It's the whole response of all the units in the network. And then there's the probability integral dr. R is a scalar, so r given x0 and y. So
Small x after the second integral?
it's no, this is a multiplication.
Multiplication. Okay.
Okay, so this is just the probability distribution, everything I wrote so far. And now I multiply this by the quantity that I want to average, which is r times eij. So d log p I of yi and given x 0 and w with respect to wij. Okay, so again, I will write explicitly the log, the derivative of the log, as a product of 1 over p times let's just write it shorthand, 1 over pi times dpi to the wij. And now you can see that there's one thing that I need to think about. When I went through my notes, I didn't realize that there's something a bit confusing here, so I need to think about it. Here we have here the whole vector of y's. I think, yeah, and here we have a particular y. So we have here the probability of that particular unit with respect to wij. I want to cancel these things, but here we have the whole, like a product over all the y's. So let me think for a moment why this makes sense. Hold for 1 minute. Okay, I think I need to, my notes are not sufficiently clear and I didn't notice this when I went through them. I will just write down what we're supposed to get, and I will have to go through this more carefully and explain this to you later. Okay, so we need to get from this point to the following, and this is the part that I'm a bit stuck on right now. What we eventually should be able to show is that this is equal to the derivative with respect to wij times the derivative times the integral dx0 dy dr p of x0 p of y given x0 p of r given y or r given x and y, x0 and y times r. Okay, and I'm sorry, I'm a bit stuck on this. There's something that I'm missing. I will need to think about it. So this is what we want to show. So I'll put here a question mark, and I owe you an explanation. This is what we want to show. But what is the right here? What is this? This is just the average of R, right? This is the whole probability distribution time R. So this is the average of R. So this is the derivative with respect to wij of R, and this is what we want to prove. But I haven't proved it. I did not prove it to you. I tried to. Okay. So now let's go back and see and remind ourselves why this is useful. And this is because, so can I erase this because I prefer to keep that. Yeah. This is useful because now what we can conclude from this is that in this update step, the average of delta wij is equal to eta times the derivative with respect to wij of the average reward. So what we're doing is we're doing gradient descent over the reward. Stochastic gradient descent, because this is true only on average. But as we discussed last time in the context, somewhat different context of stochastic gradient descent, if the learning rate is sufficiently slow, we're effectively averaging over many, many examples slowly, while W doesn't yet. We average over many examples over a set of examples over which wij doesn't yet get a chance to change much. So we're really effectively estimating well the gradient. So as eta goes to 0, we're more and more closely, less stochastically implementing gradient descent, only more slowly. Okay, so yes.
So what is, like, practically, what it means that you apply gradient descent in the average or not in the average? How does
It's
the change in the?
This you should go back to what I discussed last time. That if you look at the space of the weights, instead of going directly in the direction of gradient, you do these steps which are somewhat random. On average, they go in the right direction. Now, if the more slowly you go, you average over more and more steps, and therefore their average is more correctly in the direction of the.
It's less efficient because it's only in the average and not in every.
For one thing, it means that if you don't vary your eta while you're learning, then you will never converge to the correct weight. We discussed it last time. You will kind of hover around the best weight, or correct, I mean the best. You will hover around the minimum, the weights that minimize the generalization error, which is not what you would want to do. So having a large eta makes you go faster, but has a disadvantage that you don't precisely implement gradient descent. If eta is too large, you might really go so much in the wrong direction each time that it has nothing to do with the gradient, and by the time you reach the next example, the next example, the weights have changed so much that there's no relationship between the gradient here and gradient here. So if the learning rate is too fast, the whole thing doesn't make any sense.
But here you don't have restrictions with eta, right?
I didn't discuss what they are, but this will depend on the problem. But this property almost always exists. That if eta is too large, you're not implementing anything remotely close to the gradient descent, because it's so stochastic, and by the time you change the weights, they're completely different. If you make eta smaller and smaller, you produce a more correct approximation of gradient descent. Okay, so I want to make some comments, additional comments. One is that you can replace, in principle, if you wish, you can replace this update rule by a somewhat more general update rule, which has the following structure. So for each one of the weights, you can choose some coefficient. Let's just call it eta ij, and r plus another coefficient, which we will call bij times eij. And if we do that, if this is our learning rule, then the average of delta wij is going to be eta ij times d to the w ij of r. And this is because this term doesn't contribute anything on average, because the average of eij is 0. So it's only the product of r and eij which has a non-zero average. And while this is not precisely gradient descent, this kind of rule is still a useful rule which will improve our generalization error, because the average of r will be a sum over all the weights, the derivative of the average reward with respect to wij times delta ij, and I'm assuming here that the changes in the weights are small. And this is given by sum over I and j eta ij times the derivative of r with respect to wij squared. And so if we choose all these eta ij's to be positive, this is larger than 0. This is larger than 0, and this is larger than 0. So this rule is increasing the average reward, right? Okay, so just a small point. The more important comment.
Is there a benefit to doing it like this?
Well, sometimes somehow the sensitivity
Like either is a biological, I don't know, motivation to do it like this?
Right now I'm making this comment just as a technical comment that you can, which just means that we don't have to assume that that you implement for all the weights the same prefactor here. I think the question of whether it's beneficial, how would you choose these eta ij's, is kind of beyond what I want to discuss right now.
No, about the eta, but the bees can reduce the variance of the update.
Mm.
So in the reinforcement learning literature, it's a well-known technique to reduce the variance of the reinforced update.
I see. Right, that makes sense. So
if you choose the b to be the advantage function or something like that.
yeah, that makes sense. So we discussed only what is the average of delta wij. We did not discuss how variable it is, right? And the limit of eta going to 0, it doesn't matter because we're doing gradient descent. But in practice, if we have a way to make the variance smaller, that's good. So so this is a correct point, that by tuning the bij, I'm not going to go into the details, you can affect the variance of this quantity, and so you might be able to make it smaller. And so I think this probably also answers the question of how ideally you would want to choose all these eta ij's, that you somehow want to minimize some variance. I'm not sure which one. I mean, because there's a variance on each one of these, but maybe some variance on the change in the reward. So I'm not sure. Anyway, yes.
Why is this the average change in the
because I just calculated it. I can write the reward, the average reward depends on each one of the weights. And I can write, and all I'm doing is I'm changing the weights. So I can write the change in the reward as a derivative with respect, as long as the weights are changing a little bit, as a change in each one of the weights, the derivative with respect to each one of the weights times the change in that weight. And that's what I wrote. Okay, so another comment which is more important is that EIJ is a local quantity. And this is really the reason why I'm discussing this learning algorithm. Because you see that this is some function of the inputs and the weights, but the output of unit I only cares by construction. This is what we assumed in our network. The output of unit I depends only on the inputs to that unit. So this function depends not on all the x's. It depends on the inputs to that unit, and it also does not depend on all the weights. So we can write it down explicitly.
Why doesn't it depend on the weight?
Because it depends only on the weights that project to the unit I. So the unit I, by definition, its output is some function of the inputs to that unit and the weights associated with that unit. Okay? So that means that this function, again, is not some function of all the weights in the network and all the activities in the network. It's a function of the inputs to each unit and the weights that are associated as incoming weights to that unit. And so let's just look at some examples, particular example. The example would be a binary neuron. I think I wrote that example previously. So for a binary neuron, PI, the neuron, each unit spits out either 0 or 1. And so we need to define just what is its probability to output 1. And we said, let's imagine that that's some sigmoidal function of a linear weight over the inputs to that unit plus some bias. And so we can write explicitly what is the function which is written here. What is EIJ? D log P with respect to Wij is equal to, well, if y is equal to 1, I need to take the derivative of this function. So this would be the derivative of sigma with respect to its input. But we had take the log here, so it's the log of p, right? So we'll have here, let's define g of u to be sigma prime of u divided by sigma of u. And so when I take the derivative of log p, I will get g of the input. So this sum wij xj plus bi. I write it more large. G of u is the derivative of this sigma with respect to its input. But because we're taking the derivative of log, I divide also by sigma of u. Okay? Who asked the question? Okay. So it's okay now? Okay. So this is what we get here. I'm not done yet, right? I need to take the derivative with respect to wij of the input to sigma, and this will give me xj. Now, there is a possibility also that the unit has outputted -1. What would be the derivative of log b with respect to wij if the unit has outputted -1? So if the unit has outputted -1, what should we change? Instead of taking the probability of y equal 1, we need to take the probability of y equals -1. What is that? It's 1 minus that. So it's exactly the same expression, except when we take the derivative, that there is a minus sign. So if the output of the unit, I should put here an I, if the output of the unit is -1, the definition of d log p of y with respect to wij is such that we need to take 1 minus this. So we will have minus g of the same thing times xj. So this means that if I want to write what is eij, I need to write this if y is equal to 1, and this is y if y is equal to -1. So I can write it as yi times g of sum wij xj plus bi times xj, right? And so you see that the change in wij that we do at each step of the algorithm is just this multiplied by r. So this has exactly the structure of the kind of learning rules that I discussed when I introduced, when I discussed maybe in the first introductory lecture, I think, or at some point I discussed what do I mean by local learning rule. The change in wij is modulated by the reward. We imagine that this is some information which is transmitted to all the synapses, maybe through some neuromodulator. But other than that, everything else is local. The change in the synapse from neuron J to I is a product of the output of the neuron I, the activity of the presynaptic unit J, and some function of the total input that the neuron I receives. So the synapse needs to know something about the output of the postsynaptic neuron, the activity of the presynaptic neuron, the output of the presynaptic neuron, and the input to the postsynaptic neuron. So this it's local in the sense that it involves, if we have this neuron and this neuron, it involves the activity of this neuron, the activity of this neuron, the output of this neuron, whether now it's stochastic, so the activity and the total activation is not the same thing, right? The total activation is what's seen here. If we would look at a deterministic model, then this and this would be directly related to each other, but now it's a stochastic model. So the change that we need to do has to do both with how much this neuron was activated. Maybe this is something like the membrane potential of the neuron or the total synaptic input that it receives. The synapse does need to know about that. But that makes sense because the synapse lives on this neuron. So it's reasonable that it knows about, say, the membrane potential of this neuron. It also needs to know whether the neuron has, what exactly, given the activation of the neuron, what the neuron has done, which is this. So if we would think, like extend this to thinking about spiking neurons, this is like saying whether the neuron has actually emitted a spike or not just whether it's, what is its membrane potential.
But the change of all ways to this single neuron change together, right?
Yeah, not just to see this single neuron, to all the neurons in the network, right? All the neurons all the weights in the network are being updated each time we present an example.
But I mean, like the local thing based on the local change.
But the change in each synapse
depends on the other ways, not on all the ways.
Well, it depends not only, it depends on all the other weights because the other weights affect the activation of the neuron, and this is true. It depends also on the other weights in the network in the sense that they affect the activation of the neuron, right? Also, if we think of a feed-forward network at some layer, the activity of a neuron does depend on, is influenced by the weights all along the chain that has led to that neuron. But what all the synapse needs to know to decide how much to change is the total activation of the postsynaptic neuron.
But if you have a local, you decide how to change according to the presynaptic activity and the postsynaptic activity, but you change weights that are not related to this connection between the presynapse and postsynapse. You change all of them.
You change all of them, but each one for each. No, but again, for each weight, the rule, the change in that particular weight only involves, it depends only on the output of the postsynaptic neuron that involves that weight, the output of the presynaptic neuron that involves that weight, and the activation of the postsynaptic neuron of that weight. Okay, and on each given trial, the activity of the neuron is given by this. It's true that it's influenced by other weights, but it's known to the neuron. The neuron knows how much it's activated. In that sense, it's local. We can imagine that some mechanistic rule acting on a synapse has access, is influenced by all these quantities without some miraculous transmission of information from other synapses in the network. Except for R, which is global. Yes, absolutely. No, this is online learning, and it's stochastic. Now, one other comment that I want to make is that if you look at this rule, it only makes sense if the output of the neuron is stochastic, right? We want to ask, how much would the probability of the neuron to produce whatever output it has produced changes if I slightly change the weights. If the neuron is deterministic, then there will be discontinuities. If you change the output, the neuron will have some deterministic, the probability to output a certain output would be either 1 or 0, and most of the time this will be 0, right? I mean, if you think about this binary neuron, if this was not a probabilistic rule, here the probability we define the probability to output 1 or the probability to output -1. Suppose that we would use a binary neuron which just has a threshold, and if the input is above a threshold, it always produces 1, and if the input is below a threshold, it always produces -1. In that case, the derivative with respect to Wj almost always would be 0, right? Unless you're exactly at the decision point. So this rule makes sense only if the output of the neuron is stochastic. Or more generally, in machine learning, if the output of the unit is stochastic. So this gives you some. So essentially, what's going on is that the stochasticity, the internal stochasticity of the units, is allowing us to somehow explore how much, changes in the weights affect the reward. And so this is a nice example of why. I mean, when I discussed stochastic gradient descent in the last week, or maybe it was Tuesday, I don't remember. When I discussed stochastic gradient descent previously, the source of stochasticity was just the examples. In the reinforced learning, in the reinforced algorithm, there's another essential source of stochasticity, which is the fact that the output of the unit itself is stochastic. Okay, and that plays an important role in making this whole rule work. Maybe this is because I won't have time to start another topic. In fact, I'm already beyond my limit. I just want to say one more thing, and this is that stochasticity in neural activity is actually something that is seen during learning in the brain. And a very important or very nice example is in motor learning. So one very nice example where this has been characterized is in motor learning in songbirds, for example, which learn how to produce a very precise song. So while they're learning to produce the song, the activity in the areas that produce the song is quite variable. And we know even that there is a particular area in the brain which is responsible for generating this variability. And as the bird becomes better and better at producing the song, it tunes down the variability. So this is like, in some sense, this variability has as I mentioned, it's essential for being able to kind of explore, to change your output and see how it's affecting the reward. But it has a drawback. What is the drawback? That we're never going to produce a very well-defined output. If the units are stochastic, then always our output will be stochastic. Maybe we don't want that. Maybe we do have a behavioral output which we want. to be set in a very precise manner. This is the case in motor learning. The birds essentially learn to produce a very, very precise song. So there's a disadvantage. So one way to deal with that is to initially have a large amount of noise, which allows to converge to the best, to some optimal solution, and then while doing it, gradually reducing the amount of variability, because in the end you want to produce maybe not a stochastic output. And this is more broad. In birdsong, it has been characterized very, very carefully, and we know something about neural mechanisms that are responsible for tuning the amount of variability, but also in motor learning in humans. If you look at when humans try to learn a stereotypic action, for example, the serve of a tennis player or a musician learning to produce a sequence, and you look at the many examples where the subject is doing the same action again and again, you see that a novice tennis player has a lot of variability in their serve. And when you look at experts, say a professional athlete or professional tennis player, then the amount of variability becomes very, very small. They produce a very, very precise action. And there are experiments that show that also humans that learn in a more controlled lab setting, humans that try to learn to do some stereotypic action, initially they have more variability in their action, and you can imagine that this variability serves to allow some kind of learning on the lines of these ideas, and then gradually the amount of variability, as the action becomes more and more precise, and more correct, the amount of variability is tuned down as well. Okay, so I thought that we'll start decoding today. We'll do it on Tuesday, but with Neta, you will actually start discussing decoding in the next hour. And I remind you to discuss among you the exam. Who is taking notes today? Did anyone do it? No. Okay, I forgot to ask you to do it. So is anyone volunteering to do it, at least for Neta's?
Everyone that is not that have exams that are not the LSEC student exams to add into the list. So we are any תעזרו לי עם אנגלית אחרי זה.
נראה לי שכל מי שלא כאילו כל הדוברים אנגלית. יש איזה שעה. Do you know when your exam is?
Yes, we're still
January?
February, sorry. And when and the PhDs when
Yes,
March.
לא, נראה לי שהוא רק רוצה את הרשימה. מתי יש לי? כן, תראה לי לשאול בכל מקרה אולי כדאי באיזה דודל או משהו לשלוח לכולם שכל אחד ימלא
אני אכתוב. כן, אני אשלח למקרה שמי שלא פה ושיהיה בנחת כאילו יש משהו נורא קל בלדבר את הדברים, כי אתה יודע אם בן אדם אם תתחיל לו מבחן יום לפני המסעים זה היה או לא.
למי בעצם אולי אם חד חד
כן, פחדתי ללוך, הנה 18 בפברואר.
אוקיי, טוב לדעת. מה-18 בפברואר ועד? וזהו כאילו? ועד סוף חודש? וואלה. כל הכבוד לצה"ל. כל הכבוד לצה"ל.
מי שמצליח להוריד את המילואים, אני כאילו כמובן
כאילו זה להשתמש בתופעות.
אוקיי. ממש חשבתי אחרי זה, יכולים לדון רק מהפברואר, רק התחילת פברואר.
ויש את חונק שדחינו את זה כדי שלא יהיה בתחילת פברואר, כדי שלא יהיה
כאילו, הסיבה עד 18.
כשיש אינטגרל מגדירים את y, אז יש לך y given אצלנו, ואז כשיש את x ו-y מגדירים את r. אז אפשר פשוט לעשות את התוכלות לפי ואז אם את רוצה לדעת מה התוכלת של r, אז זה כמו לקחת את התוכלת של r בהינתן ערך מסוים של x ו-y, אז את מקבלת, כשאת עושה את זה, את מקבלת משתנה מקרי פונקציה של ה-x ו-y של x, ואז את לוקחת תוכלת של המשתנה המקרי הזה ביחס ל-y, בהינתן איזשהו ערך של x, ואז עוד פעם את מקבלת משתנה מקרי, תלוי ב-x של זה, ואז עוד אם התוכלת של x זה התוכלת של התוכלת
If you want to try it, like it's for everyone to make
18 כבר
התוכלת הפנימית כאן היא על x, לא של x, בהינתן ערך מסוים של y. ונקבל, הדבר הזה זה משתנה מקרי, שהוא לא y, כן? ואז כשאת לוקחת
כאשר ה-x'ים זה רק ממש תאריך של מבחן אחר, ולא כזה. בדרך כלל אני חוסר סיבה למנהג הזה לשנות את התאריכים של המבחנים אחרי תחילת שנה. כאילו, עכשיו אני מאלה שמתעקשים להזיז אותם שוב, אז כאילו אין לי שום זכות לא לחבב את האפק הזה. שמזיזים אותם, כאילו, בתכנון הסמסטר אני קצת מתחשב בזה.
ולא...
אוקיי, אני גם בשוק רגע.
חשבתי שאתם כותבים תרגיל.
זה אני מזהה. אתה עם מבחנים כמוהו?
בערך, כן.
יש לך עוד את זה.
אבל אני עוד לא... כאילו, אני עוד לא רשום לקורס הזה, אני במרצה.
עוד לא רשום?
כן, זה מוצא קצת מוזר.
רגע, אני גם לא יכול החל מ... טוב, אני לא רואה. החל מ-25 שנה.
לא רואה. תמיד שאמרו לשים אותו ב-12, שני אלף אופן, כאילו כל תקופה לכנות להסתכם בתוך השבוע הזה, זה יהיה פעם. אבל...
אוקיי, אז זה כזה... סוג של כלל שרשרת.
שני אלף תשלוח מהאלותי, כנראה שרוב האנשים בכלל לא מודעים לרוח שאנחנו עושים פה.
בהנחה שהדלתא עוד...
תשלח מייל ונראה מה...
זה כל המבחנים?
מה עם להחלות על הסטאט?
החל מכאן זה התאריכים שגילו יכול. כן. וזה לא כולל את רוב האנשים שלא היו היום. אני משער שחלק גדול מהאנשים שיש להם אילוצים, רוב